Assalamu alaikum and welcome. In this lecture, I will be covering some of the basics of power electronics. As we already have discussed these topics in our class before lockdown, we will only go through the gist. As a quick reminder, here is our syllabus and here's the recommended books for this course. So here is the basic diagram of a power electronic system. So here you can see the input power and here goes the output power. So there must be some sort of differences in input power and output power in terms of maybe voltage or current. So that parameters must be controlled in some predictable ways, and this processor controls these parameters. So this is the basic of the power electronics. So here is basically some of the advantages of silicon carbide as a power electronics material. So it has higher critical electrical field, higher thermal conductivity, higher operating temperature, and higher current density, which enhances the device's property. Now, here are some differences between power electronics and linear electronics. Power electronics basically deals with switching on and off. So here is basically on-off control. And in linear electronics, uh, it is all about the active region of the transistor or the amplification of the transistor. But in a power electronics device, we only concern the on and off of a switch. So this is a typical example of a voltage divider. It's a resistive voltage divider. So if we need 50 volt out of 100 volts, we can easily get it using a voltage divider network. But we have to keep that in mind that this resistance is not part of the load. So any power loss associated with this resistance, we have to consider it as a loss. So in case of this diagram, you can easily see the loss is 50%. So that brings the overall efficiency of the system below 50%. So this type of approach is not very uh, economical in terms of energy efficiency. But if we use power electronics as a voltage divider, this is basically an on-off switch. So if we concentrate on the diagram of the duty cycle diagram, so half of the time the circuit is turned off. So there can't be any power loss during this time. So you can say this type of system is very energy efficient. So here are some typical applications of power electronics. So you can see it is used pretty much everywhere in our day-to-day life. Power diodes. So this is basically the feature of a semiconductor device, uh, such as voltage rating, current rating, operating speed, and on-state voltage drop. So voltage rating and current ratings, maybe these are self-explanatory. Um, so voltage rating is the maximum voltage that the device has to withstand, and the maximum current is the instantaneous maximum current that will be flowing through that device. Switching speed is another parameter which is very important. So uh, there are different types of devices depending on the switching speeds. So basically it means uh, in terms of power electronics usage is the amount of time it takes to turn on and turn off. And another parameter is the on-state voltage, which is the measure of the voltage drop while the device is on. So these are other parameters like forward voltage drop, breakdown voltage, and reverse current. Another important parameter is reverse recovery time. So uh, this phenomena is illustrated in these two diagrams. So reverse recovery time basically means the time required for the diode or for the device uh, to fully recover. I mean, if it is subjected to a forward bias current and immediately a reverse current is applied, then it takes some time to neutralize the carriers in the depletion region. So in case of a diode, when the diode is forward biased, the width of depletion region is decreased, and when it is reverse biased, the depletion region widens. So in case of a fast transition between forward and reverse, the depletion region gets wider. So it takes some time. So that is the period we are calling it reverse recovery characteristic of a diode. So this is a quick math for reverse recovery parameters calculation. So all you have to do is remember these two formulas. Uh, it will be helpful in mathematics. So here is basically um, a definition of intrinsic semiconductor, which is denoted by this n minus drift region. So you can probably tell by the uh, sign that the doping of this n-type material is less in this area compared to this n plus structure. So less doping means less conduction. So it translates to a higher reverse voltage, but there is always a drawback, which is uh, a higher than above average resistance during forward bias condition. So which can be tricky uh, when it comes to cooling the device. So here are different types of diodes. Uh, Firstly, the line frequency or slow switching diode, which is the typical diode we use in lab, which has a typical rating of 9 kilovolt and 5 kiloamp. Another type is fast switching diode, which is used in fast switching converters. Uh, the frequency range is up to hundreds of kilohertz. Uh, but there is a trade-off between fast switching diodes and its forward voltage drop. In this diagram, this can be illustrated. So, if you follow the red curve uh, in these two diagrams, this red curve has significantly higher forward voltage compared to the forward current. But the same red curve shows a significantly lower reverse recovery time. So here is the trade-off. So if reverse recovery time decreases, the forward voltage increases, and vice versa. Another type of diode is Schottky diode, which has a voltage drop, forward voltage drop of 0.3 to 0.5 volt. Uh, Being a majority carrier device, Schottky diode can turn on and turn off pretty fast. So the switching loss is very low in case of a Schottky diode. So Schottky diode basically uh, is a majority carrier device, as there is no typical PN junction. The recovery times are much lower. Um, so Schottky diode can be very useful in case of a high frequency application, but it has some drawbacks, like it has very low reverse voltage, maybe 50 volt or less. So another improvement of Schottky diode is silicon carbide based Schottky diode, uh, which can withstand a voltage, a reverse voltage of 1700 volt, and its on-state voltage is much lower, only 1.7 volt.